Okay, maybe we can get started. Some people return, but we get started. So welcome everybody to the first talk of today's this session, the second session of today. We have Nidhi Kaihnsa from Brown University, and she'll talk to us about some topics more closely related to real algebraic geometry as against tropical algebraic geometry that we have been seeing. So it'll be on parameter estimation in chemical reaction networks. And there was also some Newton polytopes, right, in your title, or at least in your abstract that you mentioned.
Yeah.
So we'll see some Newton polytopes as well that we have been seeing in the past 2 days. So it's not very unfamiliar territory. Yeah, over to you. Yeah, Nidhi. Thank you so much.
Thanks, Madhu. Thanks for inviting me. So yes, I will talk about parameter estimation, and we'll do we'll carry out these estimations using the method of Newton polytopes. So that's basically the title of my talk. And to begin with, I will lay down the groundwork for what chemical reaction networks are. This will be a little bit of an applied talk. So basic setup for what's coming forward is a graph. A chemical reaction network is always a graph to me on various species, various chemical species. The species are x1, x2 to x5. This is an example, a hypothetical graph. And these x1, x2 up to x5 are my species. A vertex of this graph is a linear combination of species, more particularly linear positive integer combination. So the coefficients of each of species on every vertex is a positive integer, 1 and 2. The graph is a directed graph and also weighted. The weight of each directed edge is called a reaction rate for me. So in this network, there are 5 reaction rates because there are 5 reactions and 5 directed edges. And these reaction rates are from K1 to K5. Under the assumptions of mass action kinetics, with each graph, each such chemical reaction network, I can associate a dynamical system. How do I construct the dynamical system? Is basically, it is the product of 3 matrices, Px, Ak, and Y. What are these matrices? So I label each of my vertex 1, 2, and 3. So Px is a monomial matrix, and it encodes a monomial corresponding to each of the vertex. So here it is x1 times x3 to the power of their coefficients. And this one should be x2 times x5 squared, so which is this one. Ak is the negative of the Laplacian of the graph. So if you don't know what the Laplacian is, you can in fact encode this information as going from vertex 1 to 2, you write down the weight of the directed edge. So that's the entry of Ak. So 1, 2 is K1, 1, 3 is K5, and so on. And each of the row entries should sum to 0. So that gives us our diagonal entry, which is 1, 1. And this you can do again for the rest of the entries of 8. So this is basically the size of this matrix is exactly the number of vertices of the graph. Y is often called a stoichiometric matrix, and this encodes the number of units of each species on each vertex. So on vertex 1, we have 1 unit of x1 and 1 unit of x3. On vertex 3, we have 1 unit of x1, x2, and 2 units of x5. And when you take the product of these matrices, you get the ordinary differential equation corresponding to the chemical reaction network. So why assumption of mass action kinetics is, becomes much more clear if we actually see the differential equation. So when we take the product of these matrix, we'll get these equations. So what this assumption says is that the evolution of each species, the decomposition or their formation, is dependent on the product of the available concentration of those species. So along this reaction, my x1 decreases, and along this reaction, my x1 increases. So I'm encoding the change of x1 dot as minus k1 x1 x3 plus k2 x times x4. So that is what we mean by mass action kinetics. And along this third reaction, x1 again decreases, so we have minus k5 x1 x3, and we do this for all of the species, right? So we make note of where each of the species are occurring in which of the reactions, and that gives us, and using those reactions and the mass action along for the reactant complex, we create these.
So each species, sorry, go ahead, sir. Each species corresponds to a vertex, right? Is that right?
No, each complex corresponds to a vertex. So complex is linear combination of species. So this is
okay. Yes, and this matrix Y, how did you construct that again? Sorry, you just missed that part.
Right. So this is my vertex 1, this is vertex 2, this is vertex 3. And so each of the row labels vertex 1, 2, and 3. So let's just see, for the third one, we have 1 unit of x2 and 2 units of x5. So 1 unit of x2, 2 units of x5. So this is labeled with x, with the number of species. The columns are labeled by the species, rows are labeled by the vertices.
Yes, any other questions? Okay.
Okay, so this is basically the setup of chemical reaction networks. How do we go from the graph to the actual dynamical equations? Now, each of these dynamical equations, so because of the assumption of mass action kinetics, these are polynomials. And going forward, we'll treat our xi's as the variables of these polynomials and ki's as our parameters. And because these, we are often interested in biochemical implications of these equations, our xi's and ki's will always restrict them to positive real values, right? Because only positive concentration of some species makes sense, negative concentration doesn't make sense in terms of chemical reaction networks. Again, fi's are our polynomials in variables x1 to x5, and coefficients are dependent on k1 to k5. Now, often these equations, the ordinary equations, have some linear relations between themselves. So there are 3 linear relations right here for this system. x1 dot is equal to x3 dot. So these two equations are equal. And you can also see they're equal because x1 and x3 always appear, in a similar way. So there is some sort of symmetry already there in terms of x1 and x3. So x2 dot and x5, twice of x2 dot is equal to x5 dot, and similarly x2 dot plus x3 dot plus x4 dot is equal to 0. So what this means is, if there were no such linear constraints, we had these 5 variable ordinary differential equation. So our trajectory was supposed to lie in a 5-dimensional space. But because we have these 3 linear equations, if I have an initial value problem for this ordinary differential equation, that is to say, if I know I'm starting from some given point in the space, my trajectory is always going to lie in some 2-dimensional space, because my 5-dimensional space is now cut down by these 3 linear equations given by my first initial value point. Okay, so just to reiterate, that there are some linear subspace, and that linear subspace is then determined by my first initial value point that is given to me in the beginning of actually creating the trajectory, and that specifies my 3 equations and actually the subspace where my trajectory will lie. And that subspace, we often call it as stoichiometric compatibility class. Okay. Now, for these chemical reaction networks and the stoichiometric compatibility class, we are often interested in the equilibrium points of the dynamical systems. Now, what these dynamical systems are, given a stoichiometric compatibility class, we want to see where all of my right-hand side polynomials just vanish to zero in the given class. So those are my equilibrium points, and right. So for all x, such that all of my fi of x is equal to zero. What were my fi's? My fi's were exactly these, all 5 of these polynomials. Okay, so going forward, my equilibrium points, I might change the terminology. Sometimes I would call them steady states or stationary points. They are actually all equivalent terminologies. Okay, so if you didn't understand something along the line, here is one tiny example in 2 variables. So I have, let's just say I have some chemical reaction network and I get the ordinary differential equations. I have x1 dot and x2 dot. And I also have a relation, a linear relation between them. If x1 dot is given by some polynomial which is dependent on x, but is also is variable with respect to the parameters. And I have minus twice of f1x, which is my f2 of x. Right, so there is a linear relation which is given to me by twice of x1 plus x2 equals to c. Now, f1 is a polynomial in 2 variables. So basically, it's a curve. A steady state variety is the zero set of all of the polynomials, f1 and f2. In this case, it is basically a zero set of just the f1 because f2 lies in the ideal generated by f1. All right. So what are my stoichiometric compatibility classes? They're given to me by this equation with varying C. I have varying stoichiometric compatibility classes. Right, so if I vary C, these are my stoichiometric compatibility classes. I have various planes along which, so if I start my dynamics in this compatibility class, my dynamics is going to stay, my trajectory is going to stay within this class. Now, what my parameter does is my parameter changes my curve. So with varying parameters, the curve varies. If the curve varies, my steady state variety varies, right? So it could be this curve or maybe this red curve or this yellow curve. Now, if you're paying attention with varying curve, in some for this yellow curve, in every compatibility class, we only have one equilibrium point, right? Because this is zero set of my curve, zero set of f1 intersected with in which stoichiometric compatibility class we're interested in. So their intersection is exactly our equilibrium point. So in yellow curve, we have only one equilibrium point in each compatibility class. But for red curve, if I change my parameters and maybe I end up in some red curve, then we have multiple equilibrium points. So here we have 3. And this is exactly what we are interested in. This is the driving, one of the driving questions that we are interested in. So what does
yeah. Sorry, just a quick clarification. So how does your
I can't hear you. Are you saying the question here?
Can you hear me now?
Yeah.
So, how do we get these different curves? So there is this f1 whose zero locus you're looking at, right? And then your additional relation. You also have this additional relation 2x1 plus x2 is equal to c.
Yeah.
But then how did you get these red, blue, and the yellow curve?
Right. So my F1, right. So my F1 is a curve in some kappa i's in the parameters and x1, x2. So when I change my parameters, right, basically I'm changing the coefficients. So I'm changing the coefficients of the a curve in the plane while keeping the degree should be the same. Then I'm changing the curve.
Oh, yes, there is this additional parameter. Okay.
Yeah,
Yes.
maybe I should have written it more carefully.
And compatibility classes are so they how are they given in terms of so they restrict the parameter kappa I, or how does that go? That compatibility class.
No, compatibility class are constraints on just the variables.
Like the one you have written there, no? 2x1.
Yes. Right. So my F1 and F2 has this relation. So my here F2 is minus twice of F1. So that means my x2 dot is minus twice of x1 dot. So by first integral relations, you get 2 of x1 plus x2 should be equal to some constant.
Okay. And then you're also varying the kappa I, is that right? I mean, you also vary the kappa, you're varying these two parameters, kappa I and C.
Yes. So when you vary the kappa I, your curve changes. When you vary C, your points of intersection changes.
Okay. Yeah, thank you. Thank you.
Okay. Yeah, I don't know. Are there any more questions? Right. So these are, this gives us some of the driving questions. So for which parameter can the system attain multistationarity, right? Like for in this example, we had some parameter for which we only have one stationary point in each compatibility class. But for some different parameters, we have multiple stationary points. So we want to know what are those parameters which can actually give us this multiple stationary point in any compatibility, in just the existence of some compatibility class where this parameter can give us multistationarity. And the other is in the space of parameters are the regions which give us multistationarity and monostationarity connected or not. Okay, so the talk basically focuses on exactly these two conditions, particularly for phosphorylation networks. And what's a phosphorylation network? So here is one example of it. We have a protein, which is S0, and S0 has two sides where E, a kinase, comes and attaches some phosphate groups. And at a time, it is only attaching a phosphate group to one side, and it has two available sites. So we call it two-side phosphorylation network. And F comes and removes that phosphate group. To make things easier for us, there are 9 of these species: S0, E, F, ES0, S1, FS2, and we are going to label them from X1 to X9. And if we explicitly write out their ordinary differential equations, we'll find that it has 3 linear constraints, and they're dependent on 9 variables and 12 parameters, right? Because we have 12 of kappa 1, kappa 2, kappa 11, and here is kappa 12. So there are 12 reactions in this reaction network, so we have 12 parameters. So what we want to see is for what parameters do we get multiple stationary points for this particular network? Okay.
Where do those 3 linear constraints come from? You mentioned, but just to clarify.
The 3 linear constraints are exactly the ones which give you the stoichiometric compatibility class, right? So when you actually write out the equations ordinary equations. Like in this example, we had x1 dot. So this equation was equal to this equation.
Ah, okay.
So when you actually write down the ordinary differential equation for that chemical reaction network, so you will see that there are three linear.
Oh, okay. That's something, once you write down, you'll see that. Okay, even in this case, there are three. You know?
Yeah, and if you really want to see, I mean, those equations will be basically conserving the concentration of E. So so the concentration where E shows up, if you sum them, they should be equal to some constant. And if wherever F shows up, if you sum them, sum their concentration, that should be constant. And similarly for F0. Yeah, that's basically, those will be exactly the three linear constants.
Okay, okay. Thank
Right, so for example, here it will be x1 plus x6 plus x8 should be constant, and x9 plus x7 plus x2 should be constant, and rest of them should be constant. Okay, now to actually discuss about multistationarity, there is an existing result, and that's in fact our point of departure. That result is due to Conradi, Feliu, Mincheva, and Bioff. What they say is that for certain class of networks, I mean, these are basically technical conditions, but I'll get to what certain means for us. The question of determining whether this network or whether that network can attain multistationarity reduces actually to checking the positivity of some polynomial. What certain means is that class of networks where the trajectories are really bounded, and you impose that condition in some sort of technical conditions. And this condition actually holds for our two-side phosphorylation network. And the certain polynomial is the determinant of the Jacobian of the ODE evaluated at the steady states. When you carry out that, find the determinant of that matrix given by the Jacobian, that gives us the polynomial. So using the result, the relevant polynomial for this reaction network is exactly this. Now this is the polynomial in three variables, x1, x2, and x3. And we have made some transformations in the reaction rates for us to make it easier. And we have gone from 12 parameters now to 8 parameters. And some of these parameters, there were small kappas, and capital Ks are written in terms of the rest of the kappas which are missing. And whatever results in terms of multistationarity and monostationarity we form in this R8 space, we can always extend it to R12, because the fiber of the space under this map going from all 12 parameters to this is linear subspace, linear space of, I think, dimension 4 here. Now this polynomial, so we are basically interested in the positivity of this polynomial in R3, right? There are three variables, x1, x2, and x3. So this polynomial is only dependent on our three variables and 8 parameters. The coefficients are polynomials in terms of parameters, and we want to see if for some parameter values, this polynomial is positive for all positive x1, x2, and x3, then we do not have multistationarity. But if there exists some point x1, x2, x3 where this polynomial takes a negative value, then we have multistationarity for that set of parameters. Okay, I'll restate the problem statement here. So what the result of Conradi, Feliu, Mincheva, and Bioff states is that this polynomial, which we'll call now critical polynomial going forward, if for fixed parameters, this polynomial is positive for all x1, x2, and x3, if and only if the system is monostationarity. Actually, the theorem says a little bit more. in terms of when it's a multistationarity, it actually identifies in which stoichiometric compatibility class. But for now, we are only interested in determining whether or not the network is monostationarity or multistationarity. So the problem statement is this: finding the parameters such that there exists a point where the polynomial takes a negative value. If right, finding the coefficients of this polynomial, varying coefficients will give me varying polynomials. So I'm in R8 space. Each point is in R8 determines a polynomial. And for each point, we want to check whether that polynomial takes a negative value or whether the polynomial is positive on an R3 at all points. Okay. So any questions about what we're trying to do or what? Okay. So to answer this question, we take the help of Newton polytope of this polynomial that we are interested in. What's a Newton polytope? Just to recap, I'm sure you have seen it a couple of times by now. Given a multivariate polynomial, we take the exponents of each monomial and take their convex hull. That gives us a Newton polytope. So for each, here, there are 4 monomials and their exponents are 0, 0. Exponents of x2, y4 is 2, 4. x4, y2 is 4, 2, and x2, y2 is 2, 2, which lies inside the convex hull of rest of the exponents. And this triangle is the Newton polytope of this polynomial. Okay, so the main result that we'll be using often is that if this polynomial, let's say if my x2, y4 had a negative coefficient. So right now it has a positive coefficient, and if it had a negative coefficient, so what we're interested in is the sign of this polynomial. I can already say, let's say if the polynomial restrict to some phase of my whole of the Newton polytope, that means I'm restricting, let's say I consider just this phase, then I'm restricting my polynomial to just these 2 monomials. So I'm only considering the polynomial 1 plus x2, y4. So if just this polynomial attains a negative value, then I can always find a point which makes my entire polynomial go to my polynomial go to the negative. Right? So that's what this proposition says. Given a non-empty phase of the Newton polytope of polynomial P, Pf is the restriction of polynomial P to the monomial supported on that phase F. If Pf attains negative value, if the restricted polynomial attains negative value, then the entire polynomial, we can find a point such that the entire polynomial attains a negative value. Okay. Now this is the Newton polytope of the polynomial that we are interested in analyzing, right? Of this polynomial. These points, these gray points, there are 5 of these points, and there is one in the interior of this 2-dimensional phase. What are these points? These are exactly the coefficient, the monomials of the coefficients which can go to negative. Right? So I've written them down in such a way that the ones which are not colored, they will always be positive because all of my parameters and all of my variables are always evaluated on the positive of them. But these ones have a negative signs inside them. So if I pick my parameters in some special way, then I have a negative coefficient somewhere. And the ones which can go to negative are marked in gray, or black. Now, the nice thing is that these gray points are the vertices, and they're determined by exactly one polynomial in the parameters, and we'll call them A eta, and B eta is the blue point, and it is supported at a point on the inside of the face. Now, if I pick a parameter value such that my A eta and B eta is positive, then all my coefficients are positive, then by definition, this polynomial will never attain a negative value, right? Because we are only evaluating this polynomial on the positive order. We are only interested in real positive geometry here. But if, let's say, my A eta is negative, if I pick my kappas in such a way that this polynomial is negative, then some vertex has a negative coefficient, and vertex is a face of a Newton polytope. And if my face can attain a negative value, then I can find some point such that my entire polynomial attains the negative value, right? So if A eta and B eta are positive, then my polynomial is positive. That means my system is monostationary. So for whatever curves I get, they will always hit my stoichiometric compatibility classes in exactly one stationary point. And if my A eta is negative, I can always find a compatibility class where there is more than one stationary point, because my polynomial can go to negative. Okay, now the case which remains is when A eta is positive and B eta is negative. And this one is not so straightforward. So also in that case, now we are not interested in the entire three-dimensional Newton polytope, because that point is only supported in a two-dimensional phase. We are only interested in analyzing a two-dimensional polytope. This is what it looks like. And this is the point that has a negative coefficient under the constraint that this thing is always positive. So now we are in the domain in R8 space in the region where this is positive and this is negative. And we want to see when do we, so can we still classify, say something about the parameters where we get negative values and we get positive values. So to do this, I'm going to talk a little bit more, give you some more definitions here on circuit polynomials. I don't know if you have seen them so far, but a polynomial, or maybe I can stop here for a minute if there are any questions.
Yes, just going back. So you used that that lemma on Newton polytopes. That simplified your situation a bit, right? So so these two are potentially what is the eta? No, A eta, is that the symbol? A.
Yeah.
And B eta. So those are they can potentially they can take negative values, and so. So now, how do they behave in the vertices or the faces of this Newton polytope? That's something you.
So these 5 points. These 5 points are exactly the ones that have A eta as a product in the coefficient. And of these 5, there are at least 4 which are vertices. So if A eta goes negative, 4 vertices have negative coefficients.
Okay. Yes. Yes.
Yeah, and B eta is supported in the interior of a two-dimensional face of the polytope. So if A eta is negative, then we are done. Then we will get multistationarity. If A eta and B eta are both positive, then my entire polynomial is always positive. The case, so this was also already done by Conradi and Mincheva in 2014.
So, but when you restrict this polynomial to that to the convex hull of those points, those red points, those red points, basically those that have this a eta. So that does not contain this blue point.
We don't care about the convex hull. We are, I mean, just a vertex, any vertex. If any vertex has a negative coefficient, we are done. And here we are just lucky that we get 4 of them.
Okay. Yeah. Right. Okay.
And so I don't think we care about the convex hull here now.
Right. Okay. But the case which is non-trivial is when a eta is negative, but mu is negative, as in, what do you mean by positive? You mean here positive for all choices of your parameter, or for all choices of the parameter?
No, we fix the parameter and we check whether for that fixed parameter is my polynomial positive or negative. And we want to do this for all the all parameters in Rh space. Now, if in those parameters, if I pick up value of parameters in such a way, let's say, I have, so in Rh space, if I take this point 1, K3, K6, K9, K12, if I take this point, right? Now, this is my kappa 3, kappa 6, kappa 9, and kappa 12. Now, this already gives me a eta is negative. For this parameter value, I know that my polynomial will be negative at some point. But if I had taken this to be, let's say 1/2, then I need to check whether my b eta is negative, and then I want to do a little bit more of work there.
Right. Okay. Right. Okay. And why is it not straightforward? I mean, as in, you mean, why is it not straightforward? The case where one is negative, A is negative and B is positive?
Well, because the polynomial can still be negative, but I don't know for which parameters. Yeah.
And okay. Yes.
So in our Rh space, I want to find a boundary which divides my monostationarity parameters from the multistationarity parameters.
Right. Okay. Yeah. Yes.
Okay.
Yes.
All right. So about the to analyze this case, one way to do it is using circuit polynomials. What's a circuit polynomial? It's a polynomial given in the form of where I have monomials which define a simplex, and the coefficient of those monomials should be positive, and I have an interior point inside the simplex given by beta. That coefficient is any real number, right? So basically a polynomial of the form where my alpha j's, alpha 0 to alpha r, defines a simplex, and beta is in the interior of that simplex. Coefficients of alpha j's is always positive. Coefficient of real number is coefficient of the interior point can be anything. And we can, because it is in the interior of a simplex, we can always write beta in terms of some lambda j to alpha j, such that lambda j's are positive and their sum equals to 1. Now, again, in the case that we saw before, exactly the same polynomial, this is a circuit polynomial because their coefficients, the monomials, the support of the monomials define a 2-dimensional simplex, which is this triangle, and their coefficients are positive. And inside there's a point x square y square whose coefficient can be anything for now. Now, again, in this case, alpha 0, alpha 1, and alpha 2 are exactly these 3 points. Beta is 2, 2, which can be written as sum of 1/3 of each of these points. With every circuit polynomial, there is an associated circuit number, which is given to us by their coefficients divided by the barycentric coordinate given by how beta is divided amongst the three monomials which support the simplex. And the result basically, so why we care about circuit polynomials is that we get a constraint on the interior point, on the coefficient of the interior point, which determines when this polynomial can be non-negative. Right, so this is a result by Illiman and de Wolf, which says that polynomial P in this case is non-negative if and only if we get a lower bound on C beta given by the negative of the circuit number. Right, so circuit number for this polynomial is exactly 3. So negative of 3 is -3. So this polynomial is greater than or equal to 0 at all points. If I make this -4, then there exists some point for which this polynomial is negative. And if I take any number greater than -3, then it is always non-negative. Okay. So the results using this is now, you can see where I'm going with this is that I have an interior point whose coefficient can be negative, and I want to bound how much negative the coefficient of that point can be. So I divide the coefficient into 3 circuit polynomials, 2 two-dimensional simplex, these orange and red triangles, and 2 one-dimensional simplices, blue and green lines. And they give us inequality on the beta dependent on, so this comes from first circuit polynomial, this comes from second circuit polynomial, these comes from two-dimensional, one-dimensional circuit polynomials. Their power is 1/2. So we can always get these inequalities. But for this particular case, we do a little bit more. So I had 8 parameters. If I fix 6 of them and I get a slice of K1, K4 plane, and I fix the rest of my parameters, then this is what my, this is just a cartoon of what the regions would look like. So in this region, the one close to axis will always give us multistationarity. In the rest of the region, it will give us monostationarity. And this is true for any value of the fixed parameters for the remaining 6 of the parameters. You will always get such a slice, and this will exactly be the cartoon, which will look like the regions which are close to the axis will always give you multistationarity, and region inside will give you monostationarity. So using this, we in fact find the exact description, exact parameterization of this boundary. So we consider each slice, and for K, so what we do is in this region, we fix K1, or here maybe in this region, we fix K4. And for each K4, there exists some value of K1 such that beyond this, every value, for every value of K1, we will in fact get multistationarity. So basically we take this region, in this region, we fix a point and we find the minimizer of the values which give us multistationarity. And that parameterizes our boundary, and we do it for all such values here. And there is a great amount of symmetry in the network. So we exploit that symmetry to get the flip side of the boundary. And the interesting thing about this all is that this boundary is algebraic. So we do not get any analytical description. This is in fact algebraic boundary. And if we fix some values and we can actually carry out some elimination, and we can get in fact the exact description of the boundary, at least in some fixed slice of K1, K4 plane. Okay. In terms of connectivity, the region of, again, in the R8 plane. So right now here, we are saying that, this looks a little bit disconnected. That's because we are in the region where we are considering a eta to be positive, but there is also a region where a eta is not positive. But so in the overall R8 space, what we get is that region of monostationarity and the region of multistationarity is both path connected. So if you have two parameters, which is giving you two different polynomials such that they can attain some negative value at some point, you can actually construct a path in the parameter space so that each point on the path will give you a polynomial that can attain negative value. Okay. That said, so I can talk about the proof of this a little bit more at the end. I want to say something more on the n-side phosphorylation. So we saw that what the network that we were so far working with was just a building block where there was just two sites for phosphorylation which were available, but maybe the protein is long enough and there were multiple sites where some kinase can come and attach phosphate groups. And often this is in fact the case in this case of networks that in even these are the building blocks for various cell signaling processes, even in human body working through, and there are many sites which we are interested in. But with increasing number of sites, what we end up with is too many reactions, too many parameters, and too many variables to be computationally tractable, like the case of two-site phosphorylation. But the interesting part of all of this is that we can carry out some various simplifications. First observation is that we can write down our critical polynomial as a determinant of a 3x3 matrix. Doesn't matter number of sides of this network, doesn't matter how long is the how many variables we are, and that there are too many polynomials defining my ordinary differential equations. The critical polynomial is always a determinant of a 3x3 matrix. That makes it nice. What makes it even nicer is that the Newton polytope of that critical polynomial is always a 3-dimensional polytope, right? So we have reduced our such a huge problem to just analyzing a 3-dimensional Newton polytope. And what is more true is that the critical polynomial attains negative values if and only if the polynomial supported on a 2-dimensional phase of a Newton polytope is negative. Right? So for n equals to 4, this is what my Newton polytope looks like. And the red points are the integer points, which has monomials that can have negative coefficients in terms of parameters. Now, if this line attains negative values, so this line basically is just a univariate polynomial. And we can determine the positivity of univariate polynomial in terms of sums of squares already. So that case, if this univariate polynomial for each n is negative, then we are done. We know that the network can be multistationarity. But what's more interesting is that when this line is always positive, the points, the polynomial supported on this 1-dimensional phase is always positive, but something in the interior goes negative. That's the more interesting case. And in those cases, we show that in fact, we can generate some nice circuit covers that would give us sufficient conditions for monostationarity.
What is this critical polynomial? Did you define it?
Critical polynomial, so like we have the polynomial that we were analyzing for 2-side, we have a different polynomial for n-side.
Oh, that's the critical polynomial.
That's the yeah. We call this as critical polynomial. Okay, and the last thing is for all n in the parameter space, right? So the parameter space is always 6 times n. dimensional space. So we had 12-dimensional space in our two-side phosphorylation network, and with increasing n, it's it's increasing polynomially in terms of 6n is the dimension of a parameter space, and in that space, the region of monostationarity and the region of multistationarity is path connected. That analysis is also done using some Newton polytope. I can talk a little bit more about it, but it seems like I don't know how on time or out of time I am, or if there are any questions.
Any questions, audience? So, yes.
Can you hear me?
Yeah.
So these these equilibrium points that you mentioned, which are the intersections of the curves that you drew and the lines which are obtained by integrating the different. So is it the case that they are stable equilibrium? Meaning, if you drop the initial point at some place on that line, it will always go to the equilibrium point. I mean, or is it unstable equilibrium, like it will go away from the equilibrium point?
Well, so for this network, it's both. So, okay, so for two-side networks, what happens is you always have either one stationary point or three stationary points. So the case of one stationary point is monostationary and three stationary points is multistationary. And of these three stationary points, I think you can have both behaviors. At different stationary points, you can have either stability or instability. And with increasing n, it's a conjecture that the number of stationary points increase, the maximum number of stationary points is 2n times plus 1, 2n plus 1.
Nice. Okay, thank you.
And this determinantal description, is it a determinant of linear forms, a matrix of linear forms, or no?
Oh, no.
The entries of the matrix are monomials or what?
Well, the entries of the matrix are no, they're polynomials.
Polynomials.
Right, because they're evaluated at the parameterization of a steady state variety.
Okay.
No, they're polynomials.
Polynomials. Okay. So so you do you have an explicit description of this Newton polytope? I mean, a very explicit description.
Yeah.
Okay. How did you get to that? I mean, though it's a 3x3 matrix, so maybe that makes it somewhat easier. Okay.
Yes.
So you can explicitly compute the determinant and somehow get to it.
You can explicitly compute the determinant, at least in terms of, and then you can look at the highest degrees of each of the variables. So like in this direction, it's always just, so for any n, you will only get 0, 1, and 2 degree of the monomial. So that helps. And with increasing n, you will always increase along this direction. So the polytope is always a hexagon, but it will always look something like this. So just think of this as a general description. So with increasing n, maybe you will add 3 more points here, 2 more points here, and 1 more here, or something like that.
Oh, this is the two-dimensional phase where potentially these red points are.
Yes, but the entire polynomial will always go to negative if something on this two-dimensional phase goes to negative.
Right. Right. Any questions? Any other questions? Neeraj?
Yeah. So I actually, from the beginning, I want to ask in the initial construction. So what does this? So we have certain vertices which consist of a species, some integer linear combination. So how far practical it is? Can you illustrate few more examples or some settings where it is practically use it? check my question is clear.
No, are you talking about the polytope or are you talking about the stoichiometric classes?
So we started with certain vertices, I mean, some variables, then vertices of a triangle that consisted of species, linear combination. First slide, maybe first.
First page. Oh, first page. Okay, the vertices. Yeah.
Just to understand the context.
Yeah.
So can you, illustrate more about this complex and the reaction rate and what?
Okay. So do you want me to just go with the setup again?
Yeah, let's set up a few more examples where we see this for the computation or for application purpose.
Well, this is okay. So the chemical reaction network is the graph, and then we are modeling the dynamics of the chemical reaction networks using the mass action consumption, mass action kinetics. And this mass action so that's just a model according to which we are defining how the chemical reaction networks are, how if take some chemical species, put it in a box, how they will react amongst themselves. They will react proportional to their available concentrations. That's the model which is defined by the mass action kinetics. That's what it says, right? So when X1 and X3 are in my beaker, they will react proportional to how much of X1 is present and how much of X3 is present. And how fast they will react is determined by the rate of reactions, is their affinity to each other, whatever that would mean. And that is encoded by K1. So how fast they would react. And if they react fast enough, that determines how fast my X1 is being consumed. That means the rate of change of my X1 dot is minus K1 times the concentration which is present of X1 times the concentration which is present of X3.
This part is clear to me. Okay.
So this thing is obtained. So this was just the algorithm of actually obtaining, to be able to write these equations without having to do it manually by hand. And, this is just a way to put it in form of matrices and feed it to the computer given a graph structure. Okay. And that's really just, so you can show that this will in fact give you exactly these equations. And I think that's just the way to go from one to the second step to the third.
For examples, maybe
to say
a reference.
Actually, one is a reference. Other, I'm not sure the rate at which the reaction is taking place from one to another. It may not be one parameter, but more parameter would be involved with the chemical reaction if such a thing is happening.
Oh, in really happening, you
Yes,
you believe
yes.
that there'll be many more parameters.
Yes.
So he believes that in actually, in chemistry, there'll be many more parameters involved, and so his concern is whether this actually models the actual reaction accurately. That's right.
Yes.
Uh-huh.
Well, that I think depends on your model, and sometimes you often encode that information in terms of how you would want to, what would your K1 be?
Mm-hmm.
What would the value of it will ultimately turn out to be? You just encode that information in there. But I think this is just the way you, this is the choice of the model that you're working with. You can, of course, try some different model as long as it gives you polynomial equations. And yeah, there's a whole different thing. Then you might have to develop a different theory for things that are happening here. Yeah.
No, but are there actual reaction? Does this correspond to an actual reaction, or it's more a little cartoon of that?
No, this one is a little just hypothetical, just to give you what the setup is. But this one is an actual reaction, an actual setup that people work with. This reaction network is which, yeah.
So that's an actual reaction. That's maybe.
Yeah, it's a building block of an actual cascade model, which is relevant in cell signaling, which is a part of a whole big cell signaling network inside cells, even in human bodies and in various other organisms.
Oh, actually in practice, they are interested in, practitioners are interested in just analyzing this particular, this piece of it, or, oh, okay, you need not look at the entire, that big system that you mentioned. It's a part of that big system.
Oh yeah, it's a part of it. I mean, well, any reaction you pick does not, sit I mean, human body does considerably a lot of things at any given point of time. So you cannot say that this network sits alone somewhere.
Yeah. I mean, it's quite interesting. That's why I was trying to ask it.
Yeah. So he was just trying to connect with the actual situation in practice. So any other questions?
So the single polynomial, the big one, I don't remember what you called it.
Critical point.
Like that decides if there is one root or multiple roots.
Yes.
Yeah. So how is that derived? Is it some kind of resultant, or?
It is the determinant of the Jacobian of the defining ordinary differential equation evaluated at the steady states. Right, so you have this.
The xj's, and you just take Jacobian.
Yes.
What do you mean by the steady states?
Well, the steady states are also parametrized. So you don't, I mean, the steady states are, so you have these 9 equations, x1 dot to x9 dot. So you have f9 of those. So you get a 9 by 9 matrix by computing the determinant, computing the Jacobian. But of the 3 of, there are 3 linear constraints. So your trajectory, instead of lying in a 9-dimensional space, lies in some fixed 6-dimensional space, cut out by 3 linear constraints. Also, if you get the Jacobian of the exactly f9, f1 to f9, then the determinant is going to go to 0, because there are already 3 linear combinations which will go to 0 of f9. So instead of using that, instead of taking first 3 of those, you replace them with the 3 linear constraints and take, work with those and rest of the f9 of equations. And because there are 3 linear constraints, there is a parametrization of the steady state variety in terms of some number of variables. It's actually 3 variables, because there are 3 linear constraints. So you evaluate your Jacobian at the steady state variety, at the parametrization of the steady state variety, and then take the determinant.
Okay, thank you.
Any other questions? Okay. So, maybe, no other questions? Okay. So we are, slightly running out of time. So maybe the proof, I mean, Nidhi can either just share her notes, or there is a preprint already on the archive, or?
Right, yes. So this thing, the talk is based on these 2 joint works. I should have said this earlier. And they're both with the same authors. So it's with Elisenda Falud, Timo de Wolf, and Oguzhan Yurok. And Elisenda is in Copenhagen, Timo is a professor in Braunschweig, and Oguzhan is now a postdoc in Berlin. That's just it.
Oh yeah, thank you. Thank you very much. Thank you very much. Interesting talk. Any questions? Further questions? The online audience, any questions from the online audience? Please unmute yourself. Feel free to unmute yourself and ask. Online audience questions. So, one more question seemed to me initially when you mentioned about this positivity or non-negativity of your polynomials. You would have probably tried this using sums of squares, right? But that doesn't quite work here. Trying to represent your polynomial as a sum of squares it's not the sum of squares, huh?
No, not directly. No.
Not directly, but you know that it's.
I mean, no, because, well, it depends on the parameters, right? Because they're changing our polynomial all the time. And also there are parameters which will actually make it go to negative. So.
Oh, there are also parameters in. Oh, that's right. That's right. Right. And since it takes negative values on some choices of the parameters as such, as a whole, it cannot be written, right? As a whole, the entire polynomial, if we treat.
Can't, yeah.
So it's not okay. Oh, okay. So that doesn't quite really. It's not so relevant. Okay. Yeah. Any other questions? And let's thank Nidhi again for the very interesting talk.